So I hope you still have some attention for this tool, because I think this could be for KNL one of the most important tools to use that we offer, because it addresses directly to the vectorization, to the SIMD vectorization, and tries to make the process more easy and guide you through the vectorization process. So normally you read all the output of the compiler and get a little bit lost because you not know from the beginning what's the most important loop, and you have to do profiling, and then you have to see what's my vectorization features that each loop has and the important loops. And this tool addresses all these problems by guiding you through the process of vectorization. So first we start with an advisor overview. May I ask how many of you have already tried advisor? Okay. So I hope you will be motivated to have at least a look at it, because the way of using it is much easier, I would say, than using VTune. So let's come for the overview, the motivation. So probably the known factors that prevent vectorization of your code. So we might have loop carried dependencies. So we have A of I plus M and A of I on left and right side of the equation, which can, of course, when the vector length is bigger than, or let's say the offset here is smaller than the vector length, then you can have in one vector elements on the right and the left-hand side. So that is a dependency. Pointer aliasing, so the compiler does not know if it's probably the same vector on the right and left side here and after function calls. You might have function calls inside your code, inside your loop, that prevents vectorization because the compiler does not know what happens. Normally you would say with inlining you can cure that. Then the loop structure, the boundary conditions may play a role, so the compiler does not know about the boundaries in advance because it's a parameter as well. Or you have inner loop versus outer loop, or just the cost of the operations seems to be too high for the compiler, so it gives up. Next step would be, if you have vectorized loops, how do you know if they are efficiently vectorized? So what factors can slow down your vectorization? So first of all, it's the indirect memory access. And just it came to my memory when I started with HPC, the vector machines of Cray. So the cost of indirect addressing was sometimes only a factor of 2. But here it's most of the time much more than a factor of 2 to the peak performance. So you could always even gain half of the peak with indirect addressing on a Cray machine that times. But this is more impacting now. You could have the memory system latency throughput. So when you have a plain loop and a very big index here, then you can run into bandwidth problems that prevent you from good vectorization. Then you might have function calls which are serialized. So you don't know what happens in the function and the compiler either. And if it cannot inline, then these days, it can try some intermediate kind of vectorization, but it will be very suboptimal if it does not know what happens, really happens in this function call. You might have small trip counts, so it's very valuable to know about each loop, how large the trip count is. The trip count you probably heard of when you vectorize that the compiler generates 3 kinds of loops. You have the P loop in the beginning that's necessary to cope with the alignment. And then you have the loop body. That is the real loop body you are targeting for, and then you have the reminder for everything that fit the rest that does not fit into a multiple of the vector length. And so when the trip counts are small, when the trip count is very large, then these reminder and P loop might not play a role in your application. But if it's very small loops, then reminder and P loop might be important. And you might have branches that spoil your vectorization and let your code run slower than expected. Many other stuff like register spilling or floating point accuracy, FMA, divisions and squarts, unrolling, even AVX throttling. So this would be a workflow. Probably don't go in detail through it. You can read it later in your copy. It just starts here with a distinction between SIMD loop and scalar loop, and then for the scalar loop you should look for the so-called low-hanging fruit, that you just sort out everything that you can fix immediately without much work first. And on the other side, if it vectorizes, then you should look for the low-hanging fruit as well. And if you haven't done it, go to the beginning again, or then comes the deeper analysis that you look for the dependencies in the scalar loop, or for the vectorized loop, you look if it's probably memory-bound loops. Then you have to address something with the memory. Probably you have to change the algorithm to have a better stride, or change the loops here to have a better fitting stride, or if it's really a SIMD loop that works well, and probably you do some unrolling or things to increase the vectorization. So here's 5 proposed steps to the efficient vectorization of Vector Advisor. Sorry, I've taken originally there was Studio 2016 here, so it's already 1 year old, the presentation, but basically the steps and the content is valid today, and it's not much changed now. Now we're targeting already for the 2018 versions. The first step would to take a so-called survey. A survey is more or less a profiling that you just take the timing and get some basic information that comes from the compiler directly, but probably shown in a more fancy way. So you see you have the loops here. It's kind of profiling for each loop. And then you have some basic information like the self-time. Total time is when it's a dual loop, or when it does something inside the loop, then it's split here into the total time that contains every inner loop. The loop type, if it's scalar or if it's vectorized, is already shown here. And when it's not vectorizing, then it gives a little reason for that if there's a dependency, and you can go and work further on it. The next step would be to look at this guiding stuff, and you sometimes, when you hover over it with the mouse, you get some advices here. And you can now go through the advices and the guidance, and it gives you some recommendation. For example, here it's recommending, probably it found a P loop, and then it recommends you to align the memory access. So you see it's kind of an expert system where you are guided through the process of vectorization and are given automatic tips to improve it. The next step would be to look for the trip count, and you have to do another analysis to get the trip count. The reason is that in first step, when you do the timings, you don't want to interfere with the application, and you take a lightweight collection of timings that does not slow down the application substantially. And when you want to take the trip counts, you have to really instruct everything. This is so-called pin library that does an on-the-fly instrumentation and counts all the accesses and counts all the trip counts. And so this can slow down the application by factors, probably. And you should adapt your workload to that, not to wait too long. And then you get some trip counts. And if you mark it either on the GUI or have the right flag on the command line, you also get the flops. So it's also counting all the flops, all the SIMD operations, all the scalar operations, and all the flops that results from these operations. Then you get an output here with the total time and the trip counts, the iteration duration, and the call count, which gives you valuable information to decide what kind of steps you will take next. If trip count is low, you probably have to look for the peel and reminder loops, or if it's large, then you can ignore this. And how often the function is called is interesting as well. And it's not shown here, but today if you have this additional flag, then you get even a gigaflop number and the arithmetic intensity, which I will talk later on. The next step would be for the serial loops. You want to know if it's a dependency. You see here, it tells you in the first part if it's an assumed dependency, but it can do deeper analysis for certain loops, and you can see if for this workload there's a real dependency. But be careful, if it says here it's no dependency, or if it's all right, then it's only the analysis for this one workload. I would say it's more valuable if you see there's a real dependency, because then you know you have to work on it and change the algorithm to remove the dependency. But if it says there's no dependency, then you already have a good hint that there can be really no dependency. But I would suggest to have even a deeper look before really changing it by adding, for example, the pragma SIMD in front of it to force it to vectorize. The next step for the vectorized loops is to judge the efficiency of the vectorization. For that, it's crucial to know something about the memory access. So there are three kinds of memory accesses are here traced. The one is if you have stride 0, which means that you basically use the same value on and on, or stride 1 is ideal because that fits ideal into the maps ideal to the vector registers. The next step, if you have a deterministic or a fixed stride, which is here printed in yellow, shows you what's the percentage of fixed stride loops, or for a certain loop that it runs with fixed stride memory. And red is the worst kind. That would be if you cannot predict the memory access, if it's really an indirect memory access. So there you can expect the worst performance or worst efficiency of your vectorization. There's something more. If you open it, you get the GUI, you get the summary view. So just a word in between. My way of working with Advisor or even with VTune is that I'm using most of the time the command line and generate results with command line, and then take the results to my laptop and view it there on the laptop, because sometimes it can be annoying if it's in a remote cluster to start the GUI there. It's sometimes good for the beginning to work just with the GUI, and you are guided through the workflow. But if you are working on clusters, it might be good to learn more about how to use the command line interface. And when you have MPI applications and want to get traces, then you need to know about how to work with the command line interface. So this is the summary view, and you get an overview of all the vectory efficiency about the gain here. We have a factor of 2.64, which is here 66%. So this is not AVX 512. And a theoretical gain that we can reach. And then it shows us the hot loops, and you can see where we are here on the first. And here's a little bit more about the total CPU time and the CPU time in vectorized loops and outs in scalar loops, and then the efficiency. So this would be the overview of the survey. If you just take the survey here, and we had this picture smaller even before. You see the hotspots, you see the vector issues, the time, total time, the type of loops. So we have here a vectorized body and scalar loops. Here, why not vectorize the vector dependency or loop and function in loop? Don't see it. And the ISA, there was a feature before KNL could be accessed by too many people, which is still inside, that you can do multi-ISA binaries, and then you see the analysis for both kinds of branches here, which is quite nice. And the efficiency here for the loop, which is kind of a performance thermometer here to indicate where we can go on with work. The gain and the vector length is just 4 here. Yeah, as I said before, it's called here the performance thermometer. Thermometer is the efficiency, and we want to know why the efficiency is low, and probably reasons we have talked already about, and most of the time it's the memory access, I would say. So we can go on, and we can probably just order our loops by the efficiency, and then look where we have low efficiency, and go through the recommendations here. And you see that even you are given more flex, like the QOpt assume safe padding, and you can read this, and you will be guided to further documentation to efficiently work on these problems by using the vector advisor here. So where did I lose my 45% here? Was just the factors, which is just the more or less the same slide that we've seen before about inefficient vectorization. And then we can get here the further recommendations, which are linked to this typical stuff, the recommendations, and this memory stuff with the indirect address, memory access, and memory subset system latency we can get by getting the memory access pattern. And for that we have to do another run. Let me just say, the people who know VTune, you just do per experiment one project, one result directory. In Advisor, you accumulate the results in one project directory. So you take always the same project directory and accumulate it by first making the survey with the timings. Then you get the trip counts and the flop counts, and will be added to the same display that we saw before. Then we get another column for the flops and for other stuff that has been added. And if you want to take a snapshot, then it's a tool that's a knob that, or you can do it with command line as well. You can take a real snapshot of your program by generating one directory or one file that contains all the stuff of your experiments so far, and archive it. So a previous, when you finished with one step, you can take the snapshot and pull it on your laptop, and you can even view it with the Advisor on your laptop than the snapshot, because it contains, will automatically contain then the executable and the necessary source code. So that's a nice feature for taking the snapshots of documenting your work. Yeah, other things like traits, so are also mentioned here in the loop analytics section. And there is the special AVX 512 performance insight. You get this additional profiling here. You get the flops and the mask output. So it calculates for you the gigaflops with the trip count. You need to set a flag for it, but you get the gigaflops here. You get the arithmetic intensity, which will be later be interesting for the roofline analysis, which is for each loop the number of the ratio between the flops that you calculate for each byte that you load, independent from where you load it. This is the arithmetic intensity. Then you get another column for the mask utilization. So it can be that there is a mask by an if statement that masks out certain elements of your vector here and only uses part of the vector elements. So this is interesting information as well. So if you have a low mask utilization, you might think of changing your algorithm to pack your vectors more tightly. So the ISAR is shown, the efficiency, the potential, or the gain. The estimated gain are the vector length, and here's some traits where you can click on, or that gives you something to think of. So here we have FMA, and we have mask manipulations. We have here reciprocals, and we can think of doing some lower precision algorithmics here for the reciprocals. And there is some overview here about the instruction set. and it tells me, for example, that 24% of the instructions are memory instructions and 38 compute and 38 other instructions. And then you see you have here this triangle in before. You can click on it, and then it will tell you if it's scalar memory access or if it's vectorized memory access. So you get here some nice overview about the features here in your loops. Vectorization with high efficiency. So the efficiency might not be enough information because it can be efficiently vectorized, but with the low mask utilization. So it can be that you have to look at the mask utilization as well. Or another point is that you have to look if your loop is really vector bound, or if it's compute bound, or if it's memory bound. So this is another thing that you have to look and take into account. So this is the survey loop analytics here with the instruction mix. And you can click on the memory, for example, to see how this unfolds, and it tells you here 90% is only vector memory operations, and the rest here is scalar operations. And then you can go into the map analysis that shows you the memory access. And I know the code from where it is taken. And you see here it's these strides listed. You see here the source code, and it lists here the strides for the memory access. 0 is just that it's taking more or less a scalar, always the same value. And 3 is, there's an obvious explanation because it's using coordinates, and you have here three-dimensional coordinates, and you have the stride 3 for the three-dimensional coordinates. By the way, this example here is a good. It was even used to try this done the SDTL stuff for the AOS to SOA transformation. So there is a tutorial which uses this code here, which in the final step of the tutorial you apply this transformation from SOA to AOS, from array of structs to struct of arrays. So this is here the stride 3 for the coordinates, but you have here this red button means that it is indirect access, and you have an unpredictable memory access, which is the worst thing here because you have to generate more complicated code for that to cope with these accesses. And you see here the operand types is ints and here floats, operand size, okay. But then you see the aggregated footprint, and you see the number of bytes that are aggregated here with each call. And you see here only 88 bytes, but here you see for this indirect access 9 megabytes. So it's a good sign here that you have to find out how to deal with this indirect access. And it can be even shown here in assembly with the stride, the addresses, and here's the memory access. So this is very valuable to have a deep analysis of why the vectorization efficiency is is not as you would have expected, or if you would like to have it. Here's some metrics that shows you here the footprint. Here you have the unit stride, the fixed stride, and here you have the irregular access. If it's small enough, then everything should work fine. Here, if it's a big vector, you might run into bandwidth bottlenecks. Probably you have to use some kind of blocking or other strategies to cope with this memory access. Constant stride, you might have latency bottlenecks. Medium SMD, you have latency and bandwidth bottlenecks, probably. And the worst is the irregular access. Then you have a bad SIMD with gathers and scatters, I would say, has possible latency bottlenecks. And if it's big enough, then you have all kinds of bad SIMD and a latency bottleneck. So this could be one identification here with the small strides, and here with the with the big aggregated footprint, you see that you are somewhere here with the bad SIMD and the latency bottleneck. Now let's come to the roofline analysis. So we have our loops, and we want to know, see how far can we go with the loops, and what's the potential in optimizing these loops. And the roofline starts here on the right side by printing here the peak performance, floating point performance. So the y-axis is gigaflops per second, and here is the top performance. So it will be refined later by showing several kinds of top performance depending on the instruction used, but let's take here the peak performance first. And here is the arithmetic intensity, it's called, it's flop per byte. So it means when you have a loop, how many flops can be calculated per read byte. And when you're on the right side, when you have a high arithmetic intensity, then the memory system can always load all the data in the right time, and so you have no problems with the memory system, and you should go for the peak performance here of your system. When you are on the left side with a low arithmetic intensity, then you are bounded by your peak bandwidth. So it's more or less that you can take the flop per bytes value and multiply it by your peak bandwidth, and then you will go something up there to see where your kernel, what your kernel can achieve with this arithmetic intensity. So we have 3 kernels. So this one is clearly, these 2 ones are bandwidth limited, but this one is near to this roof here, to the peak bandwidth. So there's not much potential if you don't change the algorithm radically and get a higher arithmetic intensity. And for the second kernel is lower, and you see you have quite a potential here to go up to the roof here, and you can apply certain methodologies to get higher. At least you have some potential here to optimize the loop. While in that case, you have to do a real heavy lifting, or it's not possible to get much higher. So this one would be almost peak performance, which shows you then that you cannot go any further. So you can. It's probably not a good target to spend any time longer on this loop. So as I said, here for kernel 2, you have the biggest potential, and you might either get with the same arithmetic intensity to the bandwidth roof here, or if you have a higher arithmetic intensity by probably changing the structure, then you can probably even go to the peak performance. So there's a big gap for optimization. If you're in that region, you have a lower potential. So it helps you, the roofline analysis helps you to take the decision what to do next, or which loop to tackle on next. So the concept overview, the classic roofline, I have had a little look into the paper. So it's the difference is that you were taking in previous times the operational intensity, which is here how many flops you can calculate with each byte from DRAM. So I would say what the difference is later, but here it's really depends on the DRAM. And the problem is when you change the size of the data set or so, the amount of data from DRAM might change. So you have different kinds of analysis for different problem sizes here, which should be avoided in the newer roofline analysis. But in this one, it was just the operational intensity was in relation to the pure DRAM or the flops from DRAM. So if you have a good cache blocking or good reuse inside your caches, then the operational intensity would go up here. But we would prefer to have the same analysis for each code independent of the workload size. So that would mean we go to the cache-aware version of the roofline analysis, which has several roofs here. So we have the blue line is still the peak performance on top of it, but then we have here the DRAM, the DRAM speed here of 10 gigabytes per second. This is per core here, I guess. And you have the L1 per core performance, which is much higher, and you can reach much higher performance. And for example, if you have an algorithmic intensity of 1 and 10 gigabytes per second, then we should end up here at something like 10 gigaflops then. So it's just the flops divided by bytes multiplied by bytes divided by seconds. So how does it look like in the tool? The tool does everything for you automatically, and it calculates the arithmetic intensity for each loop, and then it also calculates the flops for each loop. And then it will put a little bullet here for each of your loops. And to not getting lost here, these loops are colored. So you see here the red loops are the most impacting, the using most of the time. So you are guided here which loops are most impacting. And if you have a red loop that's very low here in the diagram, it's a good candidate to look further into it and to spend more work on these kinds of loops. And it's highly configurable, so you can give your own limits, what means, what is a red, a yellow, or a green loop for you. And then you see you have different kinds of roofs here, which are different because of different arithmetics. So first roof would be here the scalar add, the highest speed that you can reach just by issuing scalar adds. Then the next roof would be the double precision vector add peak, what you can reach with just with vectorized add operations. The highest roof for the peak performance, a factor of 2 higher, is then the FMA peak, where you have really been using FMA vector operations. So you can plot the 3 roofs here, and you can plot 3 or 4 or even more roofs on that side here for the bandwidth. And it starts, of course, with the DRAM bandwidth here as the lowest line. So this is the mainline xenon here. And then comes the L3 bandwidth, the L2 bandwidth, and the highest is the L1 bandwidth. So you get the best performance when everything is really coming from the L1 cache. Yes, and to your information, if you are using KNL, you will see another line for the MCD RAM. So it will print in the MCD RAM as well, and you see what's my roof for the MCD RAM. Oops. What's now? Hans, your battery is low. Sorry for that. So the x-axis is the arithmetic intensity. So it's just the number of flops that can be calculated for each byte, where it's independent if the byte comes from DRAM or if it comes from DRAM or if it comes from any cache. So this is a difference to the classical Roofline, that it's independent of the source of the memory. And then we have different classes of applications. So, okay, sorry. I was going out of the movie. So you have different kinds of codes and different arithmetic intensities. And the best ones are, of course, the dense linear algebra stuff with the very high arithmetic intensity. So there's much data reuse. Every byte that's read is used for many calculations. Or some particle methods might have even better characteristics. Then in the mid-range, you have something like FFTs, and the worst stuff is sparse blast stuff, stencils, or latest Boltzmann methods, where you have intensities below 1, arithmetic intensities, and which means that you are bandwidth bound in these applications. So again, the ingredients of the Roofline automatization are then something about the flops. You can do, as I said before, everything with command line when you're on a cluster. And I would suggest to work with or learn how the command line works and get the results with the command line, draw them to your laptop or workstation, and then work on the graphical tool with the results. So that's, for me, the most convenient way of working. But here are the command lines, and you get a workflow if you are starting with the GUI. And the top one is the collect of survey. Next would be the trip count and the flops in a different run. Flops is currently integrated with trip counts. Yeah, it's quite demanding, and we can expect factors of slowdown for the analysis. But the good thing is that the technology is more or less independent of the platform, and you can use it on Nehalem as well as on KNL, because it uses not the performance registers like VTune, but it uses an instrumentation library based on the pin tools from Intel, which can impose other problems, because we had, for example, seen one problem where at the HRLS in Stuttgart they wanted on the Cray to take advisor trip counts, and it crashed. And my colleagues have analyzed the situation and saw that the file system of Cray did not support one call they needed for the pin instrumentation. So these are kinds very difficult to analyze, but they managed now that the trip counts can be taken on the Lustre file system of this machine. So then they got a new version that can do this. So the flops cannot be taken with VTune, for example, for KNL, but here through the instrumentation it can be taken even on KNL, which is good. Currently mapped to function loops and workloads. So we have here the total gigaflops, and then we have here split for every loop the number of gigaflops, and the arithmetic intensity is also calculated. Then it's the gigabyte per second measured and the total number of flops. So we have seen situations where the users complained that their own flop counting was a little bit different, and we are now looking into it, if who's right. And so no tool is really bug-free, so we have to check if everything is counted correctly here. So that's again the difference between survey and trip counts. What you can do here with survey the seconds, and with trip count the flops and the trip counts. Mask utilization can be very interesting. So when you compute here with full vectors, everything is okay. But if you have a condition that only 5 elements are taken out of the whole vector, then you get a reduced mask utilization, but probably a very good, the tool will show you a very good efficiency, because complying to the mask utilization, the efficiency works very well. So that's something that could be confusing, that you have a good efficiency, but because the mask utilization is low, you don't get very high gigaflop numbers from it. So one information is how to get these roofs. So the roofs are not taken from memory, or are not stored anywhere. They are measured with micro benchmarks every time you start the tool. So you have to look that there's nothing to disturb it, but it will gives us the most reliable results then here for these roofs by taking the micro benchmarks, like probably a small linpack and small DGEM, sorry, DGEM run and a stream run here to get all these roofs. So this would be again the difference between the cache-aware and the classical roofline. So here with the classical roofline, you take as bandwidth the bandwidth to DRAM only. So you measure the operational intensity, which is the ratio of flops per bytes read from DRAM. And in contrast to that is the new cache-aware methodology, which just takes the bytes that's taken from each memory subsystem. The advantage is that here you get different pictures for different workload sizes of each code. So you can take the same code and with a larger workload, but get different operational intensities for the loops. While here you get, for each workload, always the same operational intensity. Sorry, this is the algorithmic intensity. Yes, that's just repeating what we have already talked about. So how far are we from the peak? Can we do better? Where are we in our optimization? What are the limiting factors? Can be sought out by other previous analysis. That's the workload if you're working with the GUI. So it looks like vtune. You have to define the executable, the working directory, but don't forget here, if you want to see the flops, to mark this box here to get the collection of flops. And this has a flag inside the command line that does the same if you want to do that in command line. So you can do the Roofline analysis even in command line if you take a survey and the trip count with the flops and load the data into the GUI, then you can do the Roofline analysis from that. So you can even do Roofline analysis with the command line interface. So that would be the Roofline GUI. Looks a little bit confusing, but if you see here at the three lines here and click on it, you get the configuration menu. Then you can take off some of these roofs that you don't need. For example, here are all the roofs of single precision and double precision, and you can, if you know the precision, you can sort out, for example, the double and only look at the single roofs. And here, for example, if you're only interested in the relation to DRAM, if all the loops are below the DRAM roof here, then you can just exclude the other ones. It looks a little bit different. So here, when you click on the survey report, you have on the right side another big bottom that says switch to Roofline, and you can go from survey to Roofline and vice versa by clicking on this bottom on the left side. Yeah, the picture we saw in the beginning. The optimization directions. When you're here, then you can concentrate further on vectorization, probably through unrolling or on the threading part. When you're in that direction, you have to look more for the memory subsystem. And probably prefetching. So I learned that prefetching can be very valuable on KNL, and yet you should consider to use prefetching for your code if you're memory bound. Yeah, it's automated here in Advisor. So you can click on each loop here in this diagram, and then you can go to the source, the assembly, and get the recommendations and so on for the loop of interest. Here we have the on the lower left side, the purely cache or DRAM bound part, and in opposite to that, on the far left side, you have the purely compute bound stuff. And then you have something in between, like more compute bound or more DRAM bound. So you can take your decisions from where your loop lies. If it lies in any of the quadrants, then you can take different decisions on what you want to improve in the future. So here on the left lower side, you have the big optimization gap, and here on the upper one, directly under the roofs, you have, of course, only low optimization gain that you can have. We have the interactive mapping to source and performance profile. There's a synergy between the vector advisor and the Roofline. So the Roofline insights are, of course, influencing the workflow of advisor and vice versa. And so this is a good thing to include both analysis in one tool. And last but not least, we have this customizable chart. Here you see what I meant before, that you can select different roofs here, and it's covered here by that you can determine which loops should be yellow and red and so on to make analysis more easy for you. I haven't asked if this is still, because this goes quite a while, but probably because we now have the evaluations for the 18th version, you can send an email to that address here and work more closely with the developers together. I think people from NERSC also are delivering much information and like to work with these guys here from Vector Advisor. And there's a very ambitious colleague from the architect, so to say, of Advisor, who is really doing a lot of work and really alert to get the best optimizations into this tool. So it's probably worthwhile to, if you're interested, to send a request to these people here. So just in the end, so you can also, if you have this collection of loops, you can filter it by looking only at the scalar loops, and which are here to the lower ground and left with less arithmetic intensity, and the other side would be to have only the vector loops. Mask profiler, so you see it can deliver you the mask utilization, and here you see the loop that looks best from the, or looks very good from the efficiency and arithmetic intensity, or best from the arithmetic intensity, shows up to have the worst mask utilization. So you have to look at all the factors to get the complete picture here. Yeah, you have here the low population and low performance in spite of the high SEMD efficiency. Normally, you can order this by the arithmetic intensity to see goes with the efficiency, and order your loops by that. So legal disclaimer, not so interesting. Any further questions? Yes, please.
I had a question about the Roofline.
Yeah.
So how do you compute the peak bandwidth? Because, for example, if you just go for a string-like thing, you will see, for example, for the DRAM, that there is a difference between the read and the write bandwidth, which is not exactly real because of the write allocate caches. So what does Intel Advisor take into consideration for that? So because if I have a code that basically writes a lot to the memory, then I might not hit the theoretical line there, because I'm also doing some implicit loads.
Mhm.
Does this is accounted for from the cache-aware model? I understand that for the caches this doesn't make sense, but for the caches, if you are in the cache, but if you are in your workload is on the main memory, then the write allocate policy could also affect the
Yeah,
slope,
good point. But I think it's not that fine-grained, the analysis. Probably it would be a good addition to the tool to distinguish between the read and the write.
Okay.
So we
I
can make a
might
feature
try, yeah.
request for that.
I might try such an example to see if because by default you expect string, for example, when you write
Mhm.
to be memory bound. So I'm gonna try it and see if it goes exactly on the DRAM line. Okay, good.
Good point.
Other questions? All right.
So if we do some practical experiments, and if you have installed it here in one of...
Yeah, VTune for sure is installed, but the advisor I don't think is installed.
Because I think the learning curve is much steeper on Advisor than on VTune.
We'll see if we can ask.
Okay, thank you. So I hope you still have some attention for this tool, because I think this could be for KNL one of the most important tools to use that we offer, because it addresses directly to the vectorization, to the SIMD vectorization, and tries to make the process more easy and guide you through the vectorization process. So normally you read all the output of the compiler and get a little bit lost because you not know from the beginning what's the most important loop, and you have to do profiling, and then you have to see what's my vectorization features that each loop has and the important loops. And this tool addresses all these problems by guiding you through the process of vectorization. So first we start with an advisor overview. May I ask how many of you have already tried advisor? Okay. So I hope you will be motivated to have at least a look at it, because the way of using it is much in advance, because it's a parameter as well. Or you have inner loop versus outer loop, or just the cost of the operations seems to be too high for the compiler, so it gives up. Next step would be, if you have vectorized loops, how do you know if they are efficiently vectorized? So what factors can slow down your vectorization? So first of all, it's the indirect memory access. And just it came to my memory when I started with HPC, the vector machines of Cray. So the cost of indirect addressing was sometimes only a factor of 2. But here it's most of the time much more than a factor of 2 to the peak performance. So you could always even gain half of the peak with indirect addressing on a Cray machine that times. But this is more impacting now. You could have the memory system latency throughput. So when you have a plain loop and a very big index here, then you can run into bandwidth problems. that prevent you from good vectorization. Then you might have function calls which are serialized, so you don't know what happens in the function, and the much easier, I would say, than using vtune. So let's come for the overview, the motivation. So probably the known factors that prevent vectorization of your code. So we might have loop carried dependencies. So we have A of I plus M and A of I on left and right side of the equation, which can, of course, when the vector length is bigger than, or let's say the offset here is smaller than the vector length, then you can have in one vector elements on the right and the left-hand side. So that is a dependency. Pointer aliasing, so the compiler does not know if it's probably the same vector on the right and left side here and after function calls. You might have function calls inside your code, inside your loop that prevents vectorization because the compiler does not know what happens. Normally you would say with inlining you can cure that. Then the loop structure, the boundary conditions may play a role, so the compiler does not know about the boundaries. Register spilling or floating point accuracy, FMA, divisions and squarts, unrolling, even AVX throttling. So this would be a workflow. Probably don't go in detail through it. You can read it later in your copy. It just starts here with a distinction between SIMD loop and scalar loop, and then for the scalar loop you should look for the so-called low-hanging fruit, that you just sort out everything that you can fix immediately without much work first. And on the other side, if it vectorizes, then you should look for the low-hanging fruit as well. And if you haven't done it, go to the beginning again, or then comes the deeper analysis that you look for the dependencies in the scalar loop, or for the vectorized loop, you look if it's probably memory-bound loops. Then you have to address something with the memory. Probably you have to change the algorithm to have a better stride, or change the loops here to have a better fitting stride, or if it's really a SIMD loop that works compiler either, and if it cannot inline, then this stays okay. It can try some intermediate kind of vectorization, but it will be very suboptimal if it does not know what happens, really happens in this function call. You might have small trip counts, so it's very valuable to know about each loop, how large the trip count is. The trip count you probably heard of when you vectorize that the compiler generates three kinds of loops. You have the P loop in the beginning, that's necessary to cope with the alignment. And then you have the loop body, that is the real loop body you are targeting for. And then you have the reminder for everything that fit the rest that does not fit into a multiple of the vector length. And so when the trip counts are small, when the trip count is very large, then these reminder and P loop might not play a role in your application. But if it's very small loops, then reminder and P loop might be important. And you might have branches that spoil your vectorization and let your code run slower than expected. Many other stuff like